We will look at a problem cutting sheet metal, which specifies that the workshop cuts pieces of sheet metal from large rectangular sheets of dimensions 48 decimeters cross 96 decimeters. And it has received orders for 8 rectangular pieces to be cut out from these larger dimensions sheets, where 8 rectangular pieces of dimension 36 cross 50, 13 pieces of 24 cross 36, and 5 pieces of 20 cross 60, and 15 pieces of 18 cross 30. The problem is to find the least number of large sheets that can be used to satisfy the entire order. So we list down the probable combinations in which the smaller sheets can be cut out from the larger ones. In the pattern P1, we say that there would be two 24 cross 36 that can be cut out and one 36 cross 50, leaving some unused sheets. In pattern 2, we say that there would be one 18 cross 30, one 24 cross 36, and one 36 cross 50. In pattern 16, there would be 18 cross 30 sheets of 5. There would be 5 plus 3, 8, 18 cross 30 sheets that can be cut out. So what we have the problem in hand is that what would be the least number of larger sheets which can be used, which would be used to satisfy the or to satisfy the order. We draw out the pattern in a tabular form where we say that in the pattern 1 there would be one 36 cross 50 sheet that is possible to be cut out. And if you look back in pattern 1, that is what we see over here. And in pattern 1, there would be two 24 cross 36. So if we see there will be two 24 cross 36 in the pattern 1. Likewise, in pattern 10, we see the 5 18 cross 36 sheets can be cut out. So if we look over here, we see that 1, 2, 3, 4, 5 18 cross 30 sheets we are able to cut out from pattern 10. Now, in the mathematical formulation, we define the set of cutting patterns as I, and then the different sizes as J. So we have different four different sizes, and we define this set as J. And then the patterns of 16 patterns that we have found out as set of I. And then we are interested to know how many times a sheet metal is cut using a particular pattern. Integer variable x is used for that. The variable d is a demand defined for each size. And then for every pattern I, there is a cost associated. The number of size I or pattern j is defined by the SPIJ. So SP is the number represented in the table in this matrix, where one sheet of 36 cross 50 can be cut out from pattern I. So this parameter is indexed by the different sizes along with the patterns. So the constraints is that the demand has to be satisfied for each and every demand. So the number of sheets that can be cut out multiplied by the times a metal sheet is cut in pattern I, multiplied by the number of size a particular pattern of size j is to be cut, would be the first constraint, would be able to satisfy the demand, should be greater than the demand. The objective is to minimize the total cost. So we define the set of the patterns, the set of different sizes, then the cost associated with each pattern, and then the demand for each size. So for the sheet 1 type, there is a demand of 8 pieces. For type 2, there is 13 pieces. For type 3, there is 5 pieces, and type 4, there is 15 pieces. So that's how we define the data. And then the parameter of size pattern, the table that we have shown in earlier, this parameter is being declared here. So for example, of size 1 of pattern 1, we would be able to cut out only one from a metal sheet. Or 18 cross 30, we would be able to cut out 3 pieces of pattern 9. So 4, 9 would be 3 pieces. So here we see 4, 9 would be 3 pieces. So that is how the data is defined here.
In the next video, we will see how to implement this problem in PyOmo.